All right, welcome. Today we're diving into what I like to call a cosmic competition. We're going to try and solve one of the biggest, most fundamental puzzles in all of physics. You see, in one corner, you've got forces that are so powerful, they literally hold the universe together at the smallest scales. And in the other corner, you have a force so incredibly weak, it's almost impossible to measure. And yet, this massive underdog somehow ends up running the whole show. So the question is, how is that even possible?
And here it is, the central mystery we're tackling. I mean, we all feel gravity, right? It's what keeps your feet on the floor and what keeps the Earth orbiting the sun. But when you actually measure its strength compared to the other forces, it's just, well, it's laughably weak. So how in the world does it become the undisputed boss on the cosmic scale, controlling absolutely everything? Okay, so let's get right into it. The key to cracking this whole paradox is understanding that everything, and I mean everything, that happens in the universe, every interaction from a star exploding to you picking up a pencil, it's all governed by just four fundamental forces. So think of this as a showdown between these four ultimate competitors for control of the cosmos. It's kind of wild to think about, but it's true. Just these four forces explain pretty much everything we've ever observed. So let's meet our contestants, and we're going to start with the undisputed heavyweight champion of raw strength. First up, we have the strong nuclear force. Now this one is an absolute powerhouse. You can think of it like the universe's superglue. Its job is to hold the tiny nucleus of every atom together, cramming all those protons and neutrons into one tiny space. I mean, without this force, all those protons would just repel each other and fly apart. Matter as we know it, poof, it just wouldn't exist. Next up in the ring is the electromagnetic force. This is the one you're actually the most familiar with, even if you don't realize it. It's the force behind electricity, magnets, and even the light you're seeing right now. In fact, almost every force you experience day to day, like friction, or the force holding your desk together, it's all just electromagnetism working its magic on an atomic scale. Okay, our third competitor is the weak nuclear force. And this one's, well, it's a little more mysterious. Its main gig is to make things change. It's the force behind some types of radioactive decay, for example, where it can literally flip a neutron into a proton. It might sound obscure, but it's absolutely essential for the nuclear reactions that power our sun. And finally, our fourth competitor, and the star of our show, the gravitational force. This is the force of mass. Any two objects that have mass, anywhere in the universe, pull on each other. Now, here's a super important detail about gravity, a little clue to our mystery. It is always attractive. It only ever pulls things together. It never ever pushes them apart. Just tuck that little fact away for a minute. So we've met the four players. Now to figure out who's going to win this cosmic competition, we need to know the rules of the game. And it turns out the whole thing comes down to just two really important factors for each force: its strength and, just as crucial, its range. Let's start with strength, because this is where our paradox just screams at you. If we say the strong force has a strength of, let's call it 1, then gravity's strength is 10 to the power of negative 38. That's a 0, then a decimal point, then 37 more zeros before you even get to a 1. It is so mind-bogglingly weak. So how does it win? Okay, this table here has all the stats. It lays everything out. But don't get bogged down in the numbers. I want you to focus your eyes on the last two columns. Look at the one called range. See how 2 are super short and 2 are infinite? And then look at that last column, attraction/repulsion. This is where the secret's hiding. Let's just zero in on that range factor. You can basically split our contenders into two teams. You've got the short-range team, the strong and weak forces. They're incredibly powerful, but only inside the tiny nucleus of an atom. They're like kings of their own little castle, but their power doesn't reach past the moat. Then you've got the long-range team, electromagnetism and gravity. Their reach is infinite. All right, time for a quick pop quiz. Based only on what we just saw about range, which two forces are immediately out of the running? Which two can't possibly control things on the scale of planets or stars or entire galaxies? Think about it for a second. If you said the strong and weak nuclear forces, you are absolutely correct. Their arms are just way too short for a cosmic fight. And now we can get to the final verdict. We're down to just two contenders in a final showdown: electromagnetism versus gravity. Both have infinite range, but one is trillions and trillions and trillions of times stronger than the other. So how on earth does the weakest one pull off the ultimate upset? So here's the play-by-play. Step 1.
The nuclear forces are out. Their range is just too tiny. That leaves electromagnetism. It's super strong, but here's its fatal flaw. It can both attract and repel. And most big things, like planets and stars, are electrically neutral. They have a balance of positive and negative charges. So over large distances, all that pushing and pulling just cancels itself out into nothing. But gravity, remember its secret weapon? It's always attractive. It only ever pulls. So as you get more and more mass, that tiny gravitational pull just adds up and adds up and adds up with nothing to ever cancel it out. And that, right there, is how the weakest force becomes the undisputed champion of the cosmos.
So, we figured out the why, but that might leave you wondering about the how. I mean, how does a force like gravity or electromagnetism even work across the vast emptiness of space? Well, modern physics has a really cool answer. It's all done through something called carrier particles. Each force has its own special particle that basically carries the force from one place to another. And this is just a fantastic way to picture how that works. Imagine two people standing on skateboards. If they start tossing a heavy basketball back and forth, what happens? They get pushed apart, right? They've just created a repulsive force between them without ever touching. That's a great mental model for how these carrier particles work. They get exchanged between objects to transmit a force. But you know how science is? Answering one big question just reveals an even deeper, more exciting one. For years, physicists have been wondering, what if these four fundamental forces aren't actually separate at all? What if they're all just different faces of a single underlying unified force? This whole quest is called the search for a grand unified theory. And this isn't just some sci-fi idea. We've made incredible progress. We've actually proven that at the super high temperatures of the early universe, the electromagnetic and weak forces merge into one single electroweak force. Kind of like how ice and water are just two different forms of the same thing. Huge experiments like the Large Hadron Collider are trying to recreate those conditions, while places like LIGO are listening for gravitational waves, actual ripples in space-time, to understand gravity on a whole new level.
I absolutely love this quote. It just perfectly sums up the whole spirit of scientific exploration, doesn't it? Every time we push the boundaries and look somewhere new, we find things that completely change what we thought we knew about the universe. It's the thrill of discovery.
And so that's where we'll leave it. We've solved our cosmic competition, and we know why gravity always wins. But the search for that deeper connection, for that single unified force, goes on. And it just makes you wonder, right, as we keep exploring these connections, what absolutely mind-blowing discoveries about our universe are waiting for us just around the corner.